Hello.
Yes, Professor Narasimhan.
Yeah, Dev Satam, is it?
Yes, good morning.
Okay, good. Okay. I'll just put up my thing. Yeah.
Good morning, everyone. Welcome once again. Hi, Raj. Hello, Sanjay.
Hey, hi, Deepshitam.
Good morning.
Hi,
Good morning. By the way, Raj, the other tutorial also started, right? Do I have to go and check? Shashi is supposed to start that other session.
There is no one in the other session right now. I've
Okay.
spoken to Shashi, I've spoken to Gugun Thope, but they are saying they will join. And Mr. Thope said someone else was planning to start, continue where they had left out.
That must be Nirav Bhatt then, right? Gugan Tuppe and Nirav Bhatt.
No, Professor Bhatnagar, I think.
Shalabh Bhatnagar.
Yeah, I think it was. Okay, now there are people joining in. Shashi has joined in, and Vaibhav Vaishnav has also joined. Yeah, okay.
Okay.
Dr. Devasatham, are we planning to start now, or you want to wait for a few minutes?
Hello. Hi, Professor Tangirala. It's up to you.
No, I think
Time
so.
already. 11:30
Shankar. So Shankar is ready with this talk, I suppose. So today, both the sessions, Shankar will be the main speaker.
Right.
So I think if the speakers are ready, we can start.
Yeah. So Shankar, shall we get started? Maybe Shankar, you're on mute.
Is my screen visible?
Yeah. Yeah.
Okay, fine. Good morning, everyone. Today is the fifth lecture in this workshop, and we are going to now move from CISO systems to MIMO systems, which means multivariate input, multi-input, multi-output systems. But before we actually talk about how to identify such systems, we will first go through a representation of this multi-input, multi-output system using what's called a state space representation, which is a very convenient form for analysis of the system for doing a lot of things. Okay. So today, what I'm going to do is introduce the state space representation, and then talk about Kalman filter, which is used, which is a very standard thing. This is we are going to deal with a linear system, linear discrete version of representation, and then we'll Kalman filter is a technique that has been developed in the early 60s to obtain what we call estimates of the variables, state estimates, in an optimal manner, given the measurements and the model. So that's what we will first talk about, and then we'll say how this can be extended for the simple the errors in variables type of model, which is slightly different from the standard state space and the original Kalman filter derivations. And then we will show how the residuals that are generated from this Kalman filter is used to actually go back and validate the model that we have derived. So ultimately, the tie-up between this lecture and the earlier lectures is the model that we are going to obtain is from DIPCA, right? So we'll get all the model parameters, the error variances, all the useful information for performing filtering, and computing the residuals are obtained from DIPCA. Now we can go back and validate whether DIPCA has done a good job, especially with respect to model order estimation. DIPCA itself is good enough because there's a very powerful inbuilt hypothesis testing approach for estimating the model order. But in case, okay, it fails, it might fail by estimating the order slightly underestimating the model order, in which case we can catch it using the residuals that are generated. And that's what we are going to demonstrate today. And finally, in the lecture in the evening, I'm going to talk about obtaining the state space model from data. So far we have shown how DIPCA can be used for obtaining the parameters of a single input, single output system. We will show how to obtain the model for a multivariate system directly in the state space form. Okay, so once that is there, we have completed the whole story. We can just apply DIPCA for any process whatsoever, and then this residual analysis can also be applied to that multivariate system. They'll be without any change because we are using a state space representation. So with that brief background, let me actually give you the outline of the talk. I'm going to start with the state space model representation. Some of you may be familiar, but others who are not familiar with this, I'll just give you a brief introduction and then talk about the Kalman filter for obtaining the state estimates in the non-EIV case. So the state space model representation we are going to talk about in the non-EIV case and how the Kalman filter is used to obtain the state estimates. And then we talk about the filter innovations and their properties for this. And then we show how the EIV, errors in variables difference equation model that we obtained can be converted to the standard form, standard state space modeling form. And once we have done that, we can apply all the techniques that have been developed earlier in order to obtain the filter innovations. and perform what we call residual analysis. Innovations or residuals. I use the I use the word interchangeably. So I will refer to residuals sometimes, and I'll refer to filter innovations. They are one and the same. And how we can perform residual analysis for EIV model identification, and show an illustrative example to drive home point. So let's start with the generic state space model representation of a multi-input, multi-output model. So typically the discrete state space model, the discretized form of the state space model, you can also have a continuous form if you wish. You can derive this model from first principles, like yesterday Arun showed a two-tank example, and showed how you can write down the differential equations that govern the material balances for that, and then how you can linearize it, and finally you can discretize it for a given sampling period and get the linear discrete model in the input-output form. We could also get it in the state space form by defining the heights, levels in the various tanks as the states, and you can get it in this form. So the state space form has two parts. One is what we call the state evolution equation, that's given by the first equation, where X represents what we call the state variables. The state variables are some abstract notion, but it could also be real variables. For example, it could be the heights, levels in the tanks. They could be the state variables. So in other cases, it could be an abstract notion also. It doesn't have to be tied to reality. What the first equation says is how the states are going to evolve in time. Okay, so xk, the values of the states at time k are related to the values at the previous time instant, the state at time k minus 1, which is xk minus 1, through this transition matrix called A. And then the states also depend on the inputs which force the states to change. And uk minus 1 represents the input at the previous time instant, and B represents the matrix that ties the state to the input variables. And for the moment, we will not worry so much about WK. WK is called the process noise or error in our model, if you want to look at it that way, the uncertainty in the model. But if you are talking about a deterministic framework, this W can be will not be present. So there is no noise or error in your model representation. And then the outputs Y. So we are using the same symbols as before. U is the input, Y is the output, and U is multivariate. So it can have many. It's high dimensional. It's not just one variable like we saw in the preceding lectures. So the outputs Y depends on the state variables. So this is called the measurement model or the output equation. So equation 2 represents that. So the outputs depend on the states, and it may also be directly affected by the inputs at time k, and that is called a direct feedback. Typically, if there is a delay, unit delay, this term will be actually absent. This DUK will be absent, and the outputs simply depends on the states. And again, there can be noise in a stochastic system, and that is modeled by VK. So notice that in this particular thing, we are not talking about the measurements of U. So this is what we call the traditional or classical state space model, where only measurements are associated with the outputs, and the inputs are supposed to be precisely known. And therefore, there is no distinction between U star and U and U star. You could also say, why is Y star missing? I could say that if I drop VK, then that will be called Y star. So Y star contains basically the true values when all the process and the measurement noise are absent. Okay, and Y simply is equal to the truth plus the noise associated with V. Okay, as well as W if process noise is present. So ultimately, what we have is this form. So obviously, you can convert from this form to a purely input-output form by just simply integrating over time and so on. So there is a way of converting this to a standard, what we call the transfer function representation, or the input-output representation, or the discrete version, and vice versa. These are very standard. I will actually tell you how to convert from a difference equation model to the state space model, one particular form. Okay. So what are the dimensions of state variables? Hello. Sorry about it. I'm having a meeting. Okay, so the dimensions of the state variable here is n, small n, which represents what we call the order of this. You might look at it like order, state space model order. UK is the number of input variables. We have defined it as L cross 1. L is the number of input variables. M is the number of output variables. These symbols may be different from what Arun talked about. He said the total number of variables is M, I think, if I'm not wrong. So here I've used M as the number of outputs and L as the number of inputs.
Yeah, so anyway, I used uppercase M. So
yeah, okay, fine. So we are okay with that. So
yeah.
The noise terms WK here I assumed is of what's called a full rank noise. So the noise vector is also of dimension n cross 1, and Vk is dimension m cross 1 corresponding to the output. Okay. So ABCD are called the system matrices. This is a linear time invariant version. Okay, if A and B and C and D are also changing in time, then that will be a time varying system. But for the purpose of this entire workshop, we are dealing only with LTI systems. So this representation will be appropriate for us. Okay. So what are some of the assumptions made about the noise? We are going to make the usual assumptions about the output noise. For example, Vk is a Gaussian white noise with covariance matrix R. Okay. And Wk is called the process noise. That is also assumed to be Gaussian white with error covariance matrix Q. So it need not always be present. Wk may be absent, which means your state transition model is perfect. I mean, you know, purely deterministic exact evolution for the states. But in general, you might also have uncertainties associated with this, and that is handled by Wk. We also assume that Wk and Vk may be correlated, and that correlation thing at time k. For example, the instantaneous values of W and V can be correlated with a covariance matrix S. But past values, the process noise is not correlated with the past values of the measurement noise, and vice versa. So essentially, the only correlation that we are going to admit is between the noise at time k and the measurement noise at time k and the process noise at time k. That could be allowed. In the simplified form, typically S is also assumed to be 0. But I'm deliberately allowing for this because we'll see that when we deal with the EIV system, our representation actually maps into this kind of a model. And that's why I've just allowed for correlation or covariance between the process noise and the measurement noise at that same time instant k. Okay, so that's as far as the interpretation of this model is concerned. Now, the first thing that you need to actually note is that the state space model representation is non-unique. Just like your constraint model, when we wrote for the steady state case, we show that that's only a basis representation. You could take any linear combination of the constraints and it will still be valid. You can write another equivalent form, especially if the right hand side is 0, it's obvious. Otherwise, only the constant changes if there's a constant term. So that we saw in the preceding lectures, that what we get therefore from data is only one basis representation for the constraints. And same thing will be valid here. So I'm just going to first introduce that notion that the state space representation is non-unique. So for example, if you have the state space form given like we described in the earlier slide, we could define a new state x prime, which is related to x by this what we call the similarity transformation matrix T. T is assumed to be some non-singular matrix. Suppose you actually say that define a new variable called x prime, which is related to the state variables through this non-singular matrix T. So that is like a linear combination or what have you. And then you can actually replace your x by x prime by taking x is equal to T inverse x prime. And that's what this is. So xk minus 1 is represented as T inverse x prime k minus 1. Similarly, xk is represented as T inverse times xk. Okay. So xk x prime k. So the left hand side is T inverse x prime. I've taken multiply throughout by T. Therefore, you get a T in front of everything. Okay. If you just take T inverse, you'll see that the left hand side is nothing but xk. and the right hand side T inverse x prime is xk minus 1, and the rest of it is probably same as what was before. Similarly here, xk is replaced by T inverse x, what you call T x prime. I'm sorry, this should read as x prime k. Okay, I'm sorry about this mistake. I will change it. Okay, so yk will be c times T inverse x prime k. So the whole thing now you can redefine T inverse as new a prime, TB as new b prime, and TW as new w prime, and CT inverse as c prime. D is same as before, and you'll get a new state space model which is in terms of x prime. Notice that the input output model will be same for both. Okay, suppose you derive the input output model from this state space representation or the equivalent similar obtained through similarity transformation, you will find that the input output model is identical. It's just that there are multiple state space representations for the same IO input output model. That's what we want to actually think. So you can look at X as basically a basis, defining a basis for the entire what I call representation. So this has to be kept in mind, that we can exploit it for different reasons later on. Okay, so it doesn't matter how you represent the state space form. Almost, I mean, without exception, I should say that all the results that we are going to obtain, whether you do estimation with this, or whether you do diagnosis, or whether you try to construct input output models, it wouldn't matter how you represent the state space model. All similar systems will lead to the same results. Okay, so this is only, you can choose a convenient representation for this depending on what you want to do, and we'll exploit this later on in the system identification when we want to identify the state space model from data. So this is something that I would like you to keep in mind, that state space representation is non-unique. Okay, so what does state estimation attempt to do? So state estimation says, if I provide you initial estimates of the state variables and some uncertainty description about it, which is its error covariance matrix, right? How do I obtain the optimal estimates of the state variable at all other subsequent sampling instances using your model, transition model, state transition model, as well as the measurements. So you have some initial approximate idea of where you are in the beginning, and as and when you get more and more measurements, at every point sampling instant you get some measurement, can we tell you how the state is progressing, how the state is evolving? And of course, once you know how the state is evolving, you can also predict how the measurements are going to evolve, the true values of the measurements. Okay, despite the uncertainty that might be there in the model, and despite the uncertainty that might be there in your measurements. So that's the aim of estimation. And again, there are different terminologies used depending on the type of estimates you obtain. If you are obtaining estimates at any instant in time based on all measurements until you obtain until that time instant. So let's say you focus your attention at some time instant k, and you use all the measurements that you have obtained from beginning until time k and derive your estimate of xk. That's called filtering. On the other hand, if you try to predict the values state at time k using some past measurements, maybe not up to time k, but you have used only measurements up to time j less than k, then you call it prediction. And similarly, if you use also future measurements in order to infer the value of the state k, suppose you just do a batch processing, you collect all the measurements and say, I want to estimate the, suppose you collect 100 measurements and you say, I want to estimate the state at time 50 using all 100 measurements. That would be called smoothing. So typically the words prediction, filtering, and smoothing are used. Our focus will be only on prediction and filtering here. Okay, that's the two things that we look at. And also when you're looking at prediction, we will be doing what is called one time step ahead prediction. And that's something that, again, as we go through the state estimation procedure, I will re-emphasize this. So we have some initial state estimates x hat. The hat always is used to denote the estimates. And we assume that that initial estimate is unbiased for the time being. It doesn't matter if there is a bias, it usually get killed over a period of time as you get more and more measurements. Your model has to be perfect, perfectly known, but it can be uncertain. Okay, but initially for the simplicity, we have assumed that the estimates that you have of the initial state is unbiased, which means it is a reflection of the true state at x0. and there is uncertainty associated with X, your estimate, and that is defined by what we call P. Okay, P0 represents the covariance matrix of estimates X hat 0. Okay, and we, for simplicity, again, we have assumed that's normally distributed, because then you can actually give a lot of different, what I call attach a lot of meaning to the estimation procedure. What do we mean by optimality and so on? Okay, so the Kalman filter, which was probably proposed, as I said, in the 1950s, if I'm not wrong, 54, when the first paper came out, talks about this estimation, how to obtain these estimates at different time instants in a recursive manner. And that's the big thing step. It is a least squares or a weighted least squares technique, essentially. But the beauty of that is why it's popular is it's a very computationally very efficient way in which it obtains the estimates, state estimates at every time instant. Okay, it doesn't try to, for the first time, maybe they showed how you can recursively obtain it, and that makes it very powerful. So this Kalman filter obtains the state estimates by using what two steps. I want to explain the Kalman filter in a simplistic manner by using just two steps. One is called the prediction step and the other is called the update step. Prediction is saying, look, how do I go from time instant k minus 1 to k? Okay, if I have information up to time k minus 1, how do I predict the time at same time k, which is called the one step ahead prediction of the state. And then you get new measurements, you update your estimate. Okay, so you first forecast what is going to be based on the model evolution, and then you use your measurement in order to correct it or update it. So it's a predictor corrector method, in other words. Okay, so we'll see what these two steps are. I will not attempt to derive it. I will just show you what the equations are and kind of highlight some of the important points. Okay, so the way we start here is we start with what we call estimates at time k minus 1. Exact k minus 1. In fact, I think I also have to write this as filtered estimate, exact k minus 1 given k minus 1. Okay, so I'm missing the conditionality here. So please excuse me for that. So this should read as exact k minus 1 given k minus 1 and its error covariance matrix. What do we mean by k minus 1 given k minus 1? I have somehow obtained the state estimates at time k minus 1 given all measurements from initial time up to time k minus 1. I've utilized all the information available to me. That's called a filtered estimate at time k minus 1. Now, corresponding to that estimate, because I'm dealing with an uncertain system and an uncertain set of measurements, it will not be a perfect estimate of the state. It will have associated uncertainty, and that uncertainty is described by this covariance matrix pk minus 1 given k minus 1. Again, the conditionality k minus 1 is basically saying that this is the covariance matrix of this estimate, which it's a filtered estimate. Okay, so at the end of sample k minus 1, I presume I have these two pieces of information. Remember, at time step 0, I already have this information. Somebody gave it to me. Okay, so for kickstarting the method, I already have x at 0 given 0 and p of 0 given 0. Okay, that's the initial, what we call the initial state estimate and the error covariance associated with it. Right? So the prediction step says, it's a very simple thing. It says, I have this model with me. How do I obtain an estimate for the next time instant given the previous time instant filtered estimate? Right? I also given what is the control action that you have taken, because the controller is going to take some action which drives the state and the output in a certain direction. So I know what is the control action you have taken, which means uk minus 1. Again, this should be in boldface. So please excuse me, that should be in boldface to indicate it's a multivariate variable. So since you have this model, right, the state evolution model, the simplest assumption is to say the noise is 0 and use this for prediction. And that's what this is doing. So it's just saying that, look, let me assume the noise is 0 and I'll try to predict the state estimate at time k, again given k minus 1, because I don't have information at time k. I have information up to time k minus 1, which I've used to estimate this filtered state estimate, obtain this filtered state estimate. Using that, I am projecting ahead, one time step ahead from k minus 1 to k. And I'm using my model for that. But the model has a noise. For simplicity, we'll assume that the noise is 0. So in making that assumption, obviously you are increasing your uncertainty in the estimates, and we'll see how that is done. So now the uncertainty in this predicted estimates will be the uncertainty associated in the previous, the filtered estimate, that is Pk minus 1 given k minus 1, and any transformations you have done, in this case A. So A transpose represents the uncertainty related to the first term. Additionally, of course, B, U is assumed to be certain because we are dealing with a non-EAV case. So this is certain, so this doesn't cause anything. But remember, W, we have omitted, we have assumed is 0. That has an uncertainty, associated uncertainty, Q, and therefore your uncertainty in your predicted estimate, it has two terms, one arising because of the uncertainty in the filtered estimate at previous time instant, and one because your model is uncertain, right? And you have used an uncertain model by neglecting the noise, and because of that, you have increased the uncertainty in your predictions. Okay, and that's what the first thing, equation number 6 tells. It tells you what is the error variance or uncertainty associated with the one step ahead predicted estimates, which have been obtained only from the deterministic part of the model. Now, of course, in all of this, we are assuming A and B, there is no uncertainty in A and B and so on. A and B is assumed to know we know perfectly. Okay. And also we know the error variances, Q and R and so on are assumed to be given. Now, when we get new measurements, YK, which also is a reflection of the state XK, right? How do we assimilate it or into our state estimate and improve it? So in the Kalman filter, the state estimate at time K, the filtered state estimates at time K, is nothing but a linear combination of the predicted estimates, one step ahead predicted estimate, that is what is given by equation 5, plus a correction term, you can say, okay, related to what we call the Kalman gain and something called the innovations. We'll see what these innovations or residuals are. Okay, this is nothing but the deviation of the measurements from the predicted estimates. Okay, so we'll see how the deviation is defined in the next slide. But essentially, this says, look, I have some prediction, but if I take the how far the deviation, how far the predicted estimates is from the measurement, and that error is used to feedback. Just like a controller, estimator also has a feedback, and this is the feedback term to correct it. And K represents the proportionality gain, if you will, in order to do the correction. And you get hopefully an improved estimate, X at K, given K. The choice of K will affect the quality of the filtered estimate that you obtain. So the whole aim of Kalman gain is to design this K or obtain this K such that X hat K given K is optimal in some sense. So if you want to look at the simplest case, you can think of it as a weighted least squares, which combines uncertainty in the predicted estimates and the uncertainty in the residuals or the measurements in order to come up with an optimal linear combination. Or you can look at it from a maximum likelihood estimation procedure, or you can look at it as a what we call maximum a posteriori Bayesian approach. For the Gaussian case, all of these coincide, and therefore you get the same solution as long as the thing is Gaussian. If the noise is not Gaussian, then this is only an approximation. This is not the best estimate, and you'll have to do other tricks. So for the linear case, for the Gaussian noise case, you can show that this estimate that is derived from this equation is optimal in various senses. It's a maximum a posteriori estimate, it's a maximum likelihood estimate, or you can view it as a weighted least squares estimate with appropriate answer weighting, exactly as we have seen earlier, using the uncertainty as a weighting matrix, inverse of the covariance matrix as a weighting matrix for these two, the measurements and the predicted estimates. Now, given, I've still not told you what is K, that will come up in the next slide. But suppose, I mean, you know that you can derive the optimal K such that this is optimal in some sense, as we said. Kalman has derived it. Okay. Corresponding to this estimate XK, the filtered estimate, there is a error covariance matrix, which is one is the uncertainty caused by this X hat, but that might be improved. The uncertainty is reduced because you have more information coming from measurements, and therefore it will get reduced by a certain term, and you can show that this term essentially is given by the state transition matrix, the measurement matrix, the covariance between the process and the measurement noise, and so on. Okay, and that will give you, and V also will define what V is. V is the uncertainty associated with the what we call the residual term. So this is derivable, that the uncertainty associated with the filtered estimate can be derived from the state, the system matrices, the cross covariance matrices, and the error covariance matrices Q and R. Okay, and now you manage to go from x hat k given k minus 1 given k minus 1, the filtered estimates at time k minus 1 and its uncertainty. You manage to derive the filtered estimate at time k. Now you can proceed to the next time step, applying this, moving one time step at a time. And this is the recursive nature of the filter. Okay, that's a very quick thing. I am not trying to derive it. I'm just telling you how to interpret it. Now, what are these new Ks and so on? This is known as the innovations of the Kalman filter, and we will call them residuals also. That's nothing but the difference between Y, the measured value. Of course, there is a direct feedback from U that is also subtracted, because that is a constant term. You can look at it as a constant which you are removing, minus the predicted measurements using the predicted state at time k. So remember, x at k given k minus 1 is a prediction of the state variables at time k given all the information up to time k minus 1. Using that, if you post multiply by c, remember y is nothing but cx plus du, right? Du has been taken out. Cx is also now taken out. That's why this is called the residual. Okay, so the predicted state estimates at time k is used to derive a predicted measurement. Okay, and this is the prediction. The combination of these two gives the predicted measurement, and that difference therefore represents the what we call the residuals or the innovations. Okay, and the covariance matrix of this, or the uncertainty associated with this, can be shown to be equal to this, which is nothing but depends on the measurement matrix C, as well as the uncertainty in the measurement model, which is R. And using this, you can actually obtain what's called the Kalman gain, which can be computed. So the steps for doing this thing is, first you compute x hat k given and pk given k minus 1, x hat k given k minus 1. That's straightforward. Then you compute what's called the Kalman gain, that is compute V, and then compute the Kalman gain. Remember, it all depends on what known quantities, and therefore you can compute V and K, and you can compute also mu K, because that's all dependent on known quantities. Once you have all this information, you can compute x hat k given k, and you can also compute pk given k. So you can actually go to the from time k minus 1, you have gone to the time k, obtain filtered estimates and its error covariance matrix, right? So that's your two-step thing, and the most important thing is the Kalman gain and the innovations, and we have derived them from the matrix, and this is the optimal Kalman gain from various, as I said, using various criteria you can do. So you can also prove one interesting thing, that these residuals nu k, which are called the innovations, also follow Gaussian. It's a Gaussian white noise sequence with error variance Vk. Okay, so although the Vk changes with time, okay, so you can show that the uncorrelated sequence, and it's also normally distributed, and that's what this is saying, and it has a zero mean. Now, provided all the other assumptions regarding noise holds, we have assumed that the Wk process noise and the measurement noise are all Gaussian white noise, and from there you can derive this. Now, the interesting part is, if you let it go for a long k, for a time invariant system, the k will reach a steady state value called k infinity, and p also will reach a steady state value called p infinity. And most people, if you want a quick implementation, will not do this, because you will directly compute k infinity and p infinity. There is a method for computing that, and directly use k infinity and p infinity, and the approximation will not matter very much, because in a very few time instance, the k and the p will converge. Within 5 to 10 time instance, typically k and p converges to the steady state values, to their steady state values. That doesn't mean that estimates reach steady state. Estimates will keep varying because the state is varying. The gain and the covariance matrix reach a steady state, and you can use that for analysis and for a variety of purposes. Okay, so if p reaches a steady state, v also reaches a steady state. So this will be just a v. you can use. Okay. So all we need in order to apply this is the covariance matrices corresponding to the measurement noise, or the cross covariance matrix between process noise and measurement noise, and the process noise matrix covariance, error covariance matrix Q, and the system matrix is ABCD. With that, we are done basically. And some initial estimates, if you have for kickstarting the whole procedure, you can keep applying them. Okay. So we will do this, and we'll use the innovations and their property for model verification. Our purpose is not to do purely filtering. The Kalman filter is very useful in diagnosis. For example, if there's a measurement bias, you will see that the innovations will become biased. And you can use that as a way for figuring out which of the measurement is biased or what's happening. You can do a lot of diagnosis using this analysis of the innovations. That's why it plays a very important role. Okay, and we have, I mean, this is very, again, in the diagnosis literature, you'll see a lot of people doing a variety of things with these innovations. Okay. Now, at this point, let me take a break, small break, and ask, see whether there are any questions. Are there any questions that that you want answered up to this point?
Hello, Professor Narasimhan.
Yes.
This is Devasattam.
Yes.
Just one thought that I've always been bothered about with this with Kalman filtering. Maybe it's a very simple thing. I just didn't get the time to work it out. So I always felt that in absence of noise, the Kalman filter should reduce to a Leuenberger observer, right? Does it really happen?
No, Leuenberger observer, yes. They actually, see, in the Leuenberger observer, you can design the observer in various ways. You can do pole placement strategies and so on, just like you design a controller, right? And you can suppress or highlight whatever you want, right?
Yeah.
So depending on the design, it may or may not. It may not give rise to the Kalman filter. So it depends on, because the criteria used is quite different. But if you do something like a least squares, right? Remember, when you do least squares, uncertainty is important. If you use, let's say, total least squares, right, versus weighted least squares, the results will be different, right? Here, there is a proper weighting that is done based on the uncertainty in the process noise. Basically, Kalman filter says, look, give me a model which is uncertain, but tell me how much is your uncertainty there. Give me measurements and tell me how much uncertainty is there. Then I'll appropriately weight them to get the optimal estimates. So it is a weighted total least squares, okay? Weighted least squares. I don't want to call it total least squares, because when we look at input errors, we'll call it total least squares. Otherwise, I won't call it. It's a weighted least squares approach. Whereas Leuenberger observer is actually a design. You want to design the thing in order to get some properties of your residuals or estimates and so on. So it may or may not, right? Because there you're not even using the information related to the noise characteristics.
Yeah, in Leuenberger, it's the question of placing the poles of the observer sort of remains open-ended. There's no fixed. I mean, that can be, those poles can be placed anywhere on the left of the complex plane. I mean, in the left side of the
so you want to get a stable filter in some way. That's all, right?
Right.
Stable observer.
Kalman filter, in a way, gives us a recipe of placing those poles. If we use the
it's a very specific thing. Yeah, you might say it's a very specific, which uses the uncertainty information.
Yes.
So if I can add.
Go ahead, Arun.
To the answer. So the Leuenberger observer and Kalman filter share the same concept, which is giving feedback to the state estimator through the measurements. Okay, so the idea is the same. You will still use the observations as a source of and use that as a feedback to improve your state estimate.
Right.
But and that's a concept, and as Shankar mentioned, you could, in fact, Leuenberger observers are even designed for noise-free systems.
Yes. That was my initial question.
Yeah, originally it was conceived for noiseless systems until Kalman filter came about. There was no formal way of incorporating the noise characteristics into the observer design. But the main thing that governs Leuenberger observer is that you will use the feedback from the output. You will use that to improve your state estimate at the next instant. And that same concept prevails in Kalman filter as well. That there is no difference. But the two prime differences are, one, taking into account noise characteristics or uncertainties in the state and output on the measurements, and two, the criterion for design.
Right.
Okay, so in Leonberger observer, basically one of the most popular ways is pole placement, using which you not only design a stable state estimator, that means you make sure that the error goes to zero, but also you control the rate of convergence of the error.
Correct. Yeah.
So these are the two things, and you explicitly do that by pole placement. And I don't think the question of whether it is optimal over all noise realizations and so on was not discussed. As I said, it was primarily for deterministic systems.
Correct.
I think what Kalman filter came about is handling the noise or the uncertainties. And again, Kalman filter itself today, for long it was certainly believed, and it is true that it was inspired from Wiener filter. But today it is also considered as a special case of what are known as Stratinovich filters. So Stratinovich was a Russian scientist. So he came up with nonlinear filters, and Kalman filter is considered to be one special case of that. Apparently, Kalman himself met Stratinovich in his early days of filter development. So Stratinovich papers appeared in mid-50s, and Kalman filter came about in 1961. It's also called Kalman-Bucy filter. And
interesting.
Yeah, and another viewpoint is that Kalman filter is considered a special case of sequential Bayesian estimation, because Kalman filter itself is in the Bayesian frame.
Yeah. Right.
Okay, so today, in retrospect, Kalman filter is considered to be special cases of quite a few different, more general filters.
Good. Very interesting.
Okay.
Just as a kind of additional thing, you can look at this feedback design, right? You're doing a controller design, right? This is also proportional feedback, and that also is proportional feedback. Both are proportional, but the proportionality thing is being designed differently. That's right. Another simple way of just looking at the whole thing.
Yes.
Yeah.
And one more quick question.
Yeah.
It will not take much time. So if practical implementation, when if we use a steady state filter to start with, I mean, we just use only K infinity. Okay. We don't do the sequential part.
Yeah.
How does the performance differ from this sequential design, like solving the algebraic Riccati equation as opposed to solving the difference Riccati equation? How much difference?
For LTI systems, it really does not matter.
Hardly, any difference.
Yeah,
just only the first few measurements.
That's all.
What you call, there'll be slight differences, but otherwise, after some time, like I said, 5 or 10 measurements, it converges to the thing steady state. So for most practical things, when you are dealing with large samples,
people implement only the steady state Kalman filter.
Yeah.
For the dual problem of LQR, for the dual problem of LQR, the difference Riccati and the algebraic Riccati actually makes a lot of difference, right? Because difference Riccati is for the finite horizon LQR problem.
Correct.
Whereas the algebraic Riccati is for infinite horizon.
Correct. Absolutely. Yeah. For LQR, yes, it does make a difference. But for Kalman filtering, typically for LTI systems, we implement the steady state versions only because it converges pretty quickly.
Okay.
But for LTV, of course, you'll have to implement.
In any case, today, computational advance, in the 1960s, 50s, all these made big difference because you want to save on computation time. Today, it makes little or no sense. Everybody wants to increase the cover thing because they are powerful things. I mean, they will have neural networks having millions of nodes and so on. So, I mean, this whole discussion about whether should we save a little, unless you're dealing with extremely large data, many of these things that we talk about computational advantages disappears quickly, right? I mean, really becomes a non-issue. So I think, that those are, it doesn't make, the approximation does not lead to much what I call deterioration in performance, whether you use the innovations in diagnosis in whatever thing you want to do. Okay. So good. I mean, I think, can we proceed then?
I guess we don't have any more questions from the participants.
Yeah.
Because I don't see any raised hands.
Yeah.
Perhaps we can proceed.
Okay. So let me continue. I think, where are we in terms of time? Yeah, I think. our purpose today is basically use the what I call first do the version of what we call EIV-Kalman filter. We'll show how first the DE model that was developed earlier, okay, or identified using DIPCA, can be converted to a EIV state space model, and then from there to a standard state space model for which you can apply Kalman filter and so on. Right. So here is I start with the generic difference equation model for a CISO system where we have Y stars. Now I am actually distinguishing between measurements and truth, because we are going to have measurements associated with both the input and output. So let me do it the usual way. Start with the distinction, and we have this difference equation which is representing the true evolution or the true relationship between Y and U. Y star and U star. Okay, that's why we are thinking. And this is I've used eta as the process order, and I've just not worried about which of these elements, what is the delay, and so on. So some of these coefficients may be 0, but it's a generic representation I've used. Now, in order to convert it into a state space model, one possible representation of this deterministic model, right, is to actually use what's called a controller canonical form, where you can choose your system matrix A like this, using the coefficients of A, and the rest are all unity, and then the last column thing is 0, and the size of this is equal to eta, basically as many as the number of elements here, okay, of Y. So Y1, YK basically is the first row, YK minus 1 second row, you can say roughly, and this YK minus eta is the last one. So eta plus 1. So sorry, it's eta plus 1 dimension by eta plus 1. That is your dimension of A. B is eta plus 1 times 1, because there's only one variable here. Am I right? No. Again, yeah. This is U star K minus J. Okay, let me see what it is. Okay. I should probably, this is actually one, the output is only, because we are writing this as only one output. Sorry about that. So the left-hand side is 1 cross something. So this is, am I correct about this?
Yeah, this is fine, Shankar, but B should be.
Right. Sorry.
But B should be 100. B should be 100, not B10.
B100 only.
The controller canonical form.
Controller canonical 1, no?
So B is 1. The first element is 1.
B naught is 1, but B1 is not 1. So I will check this. B naught is in D. Okay.
No. I'm saying the first element in B is 1. The B matrix, the B matrix.
No, B matrix, I'm sure I'll check this, but I don't think this is wrong. So I will check this, because B naught appears in D. It doesn't appear in B, the matrix B. So let's actually keep this, because I think this is right. What I've actually obtained is correct. But I will double check this whether there's an error. But essentially, this is n states, whatever, or eta plus 1 states related to this value. I'm just trying to see which U it is. Does it actually have a meaning of which U is this? I'm not clear. UK. Oh, yeah, obviously. See, in the state space form, if you go back, I have to have UK minus 1 only, right? So I have to relate all the states in terms of UK minus 1, and that's what this B transformation allows you to do. Once you have defined whatever states, the states themselves, as I said, are abstract. It need not be either U, Y, or U, but some combination of Y's, for example, it could be. So the state space transformation from this discrete form to the state space form is of this nature. And the way you get these coefficients is if you obtain the
Shankar. So what I was trying to tell is that this controller canonical form, the B matrix, the first element is not B1, it is 1.
Okay, that looks like a scaling factor. So I'm
not. No, it is not. It is 100. The rest of the matrices are correct.
Okay, fine. So this will be 100, is it? Okay,
yeah, that's all. Because in the observer canonical form, C will be 100.
Okay, fine.
The rest of the matrices are fine.
Okay, fine. So I'll correct this. If I'll cross check this and correct this, because this I took it from the paper, our paper. So I
think there's a mistake in the paper.
Okay.
So in my book, the correct form is given.
Okay. So the key is here. This input-output form is converted to this state space form with eta plus 1 as the number of states, right? I mean that's basically what it is doing. And in order to obtain these coefficients, what one can do is get the Z transform representation of the input-output model and do a polynomial division, and you will actually end up getting these coefficients by matching, okay, matching terms. So there is a straightforward way, but MATLAB provides inbuilt functions which convert from difference equation or an input-output model to a state space form and vice versa. So both are possible. Continuous to discrete to discrete state space. You can do this transformation. Continuous to discrete, yesterday you saw, Arun did it. But converting to state space form, there are inbuilt functions if you don't want to actually know. But you can derive. There are several ways again of doing this. This is only one form. As I said, the state space representation is not unique, even though the input for any given input-output form. There are multiple ways of doing the state space representation. Now, therefore, now if you look at the what I call the deterministic part of this EIV model, if you say state evolution, that's given here. Essentially, there's no process noise notice, there's no measurement noise. The way we actually look at the EIV case, we write the measurement model separately for outputs, which is, it should read as yk is y star k plus epsilon yk, sorry again, and uk is u star k plus epsilon uk. So these are the measurement models for input and output measurement with the usual assumptions that you make regarding these epsilons, that they are Gaussian white noise sequence and so on. Okay. So this is we have separated the deterministic, if you will, this what I call the evolution and the measurements that are related to both input and output. Okay, that's how we have done this. Now, if you want to convert this to a standard state space form, what you do is just plug in u of k minus epsilon uk for u star k, right? Or u star k minus 1 is u of k minus 1 minus epsilon u k minus 1. And so b times epsilon u will actually be now reflected as process noise. Measurements themselves is y star. You can replace y star here by y and add epsilon eq in order to what I call or rather you put y star k in this equation 16 and you'll get the measurement model for yk, and that is what I've done here. Okay, so I'm sorry, I've written it in standard form, so I've used the term w and v, but v is now nothing but the contribution of error in input DEU plus the contribution of error in y, which is EY. Again, these are all should have the rotation for each k. So I've written it in some generic form, if you will. I've forgotten. I mean, a lot of the places I've missed out the k. WK is nothing but minus BUK. That is only a contribution from the uncertainty in the measured value of u. Now, if you look at this form, this is a standard state space model with process noise, which is actually basically coming from the input measurements, if you will, and the matrix B, and a measurement noise and Y, which is contributed both because of the direct feedback, uncertainty in U, as well as measurement uncertainty in Y output. So that combines together to get this B. Okay. So now for this form, you also notice that W and K, V are not uncorrelated. They are correlated because they share a common term epsilon U, and that uncertainty is basically given by that covariance is given by this term, okay, which is BD transpose. That's because there is a cross covariance between WK and VK, okay, through EU. That is what is actually contributing to this cross covariance. So that's why we actually in the Kalman filter, I didn't use the standard what I call the simplified form where S is 0, because I can now use the general form to handle the EIV formula, state space form, right? The converted from the discrete model, we have converted to a standard what we call state space form, in which the process noise and the measurement noise are correlated, and the correlation thing is also known. So notice now, when I do the system, the identification of the model from using DIPCA, we get estimates of sigma squared epsilon U, sigma squared epsilon Y, and all the A, B, C, D can be computed from the model parameters A's and B's, small A's and B's. So pretty much everything is known about the system now from the identified model. Okay. So that's basically the representation itself. Once you have done this representation, you are now can go ahead, apply Kalman filter and obtain the residuals and so on for this. And we'll use it for a very specific purpose. So that's as far as the step for converting the DE model into a standard space plane model. Now I'm going to take an example, and I'm going to do this.
Sorry to interrupt. Sorry to interrupt.
Yeah.
In this, that S equals this expression. Sigma epsilon y square, is it a matrix?
No,
Looks like a
for the
scalar,
CISO
no?
system. I'm doing it only for the CISO system, right? That is why.
But then with this BD transpose is a matrix, right?
Yeah. Those are because those are number of states that I'm using is actually the order plus one, right?
No, we are kind of adding a non-square matrix with the scalar.
No. It won't. No, this is not a scalar. This is just a scaling factor.
No,
Sigma
Shankar,
square epsilon.
what he's asking is the first term sigma square epsilon u times BD transpose.
Is a matrix.
It turns out to be a matrix, but it doesn't, because if you look at the dimension of D transpose, D is actually a scalar.
WV.
Yeah.
Okay.
So what his concern is, overall the product sigma square epsilon u times BD transpose turns out to be a vector.
Yeah. That's okay. Right.
It's a vector, and you're adding a scalar to a vector, so that's where this concern is.
You mean okay. Oh, this term. Because this is actually 1 by.
No, this is vector. B is actually a vector.
Okay. Oh, B is a vector and D is also a vector. Oh, okay.
No, D is a scalar, but in the end, the first term is a vector.
Okay, I'll have to see this. Okay.
Yeah. So this will be.
No, it might be DB transpose. It could be that now I'm kind of slightly. I just pulled out some terms. Maybe that's the only reason I can see.
So S is the covariance between V and W.
Between V and W, yeah.
Yeah, it will be a vector if it is covariance between because
W, yes, it will be a vector. Yeah.
Yeah, it has to be a vector.
So I think it will be the second term has to be some kind of a vector.
It will be okay. Fine. The second term might have a what I call sigma square epsilon u added to all of the terms. Is it?
Yeah.
That could be.
1, 1, 1, 1, 1, 1, 1.
Yeah. Sorry. Yeah. Okay. Fine. So I need to actually correct that. Okay. Fine. Thanks. Yeah. So, but that is basically derived from these two. What WK is and B is, and you can actually from that one should be able to derive the thing. And I think I think this first of all this epsilon y
Actually,
may not
sigma
be there.
square epsilon y should not.
Why
be
may not be there? Yeah.
It's not there. It is zero. Because epsilon u and epsilon y are uncorrelated.
Uncorrelated. So this term itself will not be there.
Yeah,
Sorry about
that is
that.
wrong.
Okay. That's not there. Okay. So in trying to simplify some terms, maybe basically I introduced this error. So that term itself is not there. So it's just sigma squared epsilon u BD transpose. That's all there.
That's all it is.
That's all there is. Okay. So with that, I think essentially you have the state space representation, which allows you to apply Kalman filter to this and also produce residuals. Now let's take this example, which yesterday I think I don't know whether this is the second order example that Arun used, but we have simulated this like what you call like usual, generated PRB as signal for U, a full band, 1020, 23 samples, and use the variance of sigma squared epsilon U to be close to 0.1 and close to 0.56 for sigma squared epsilon Y. And typically that gives you a signal to noise ratio of approximately 10 for each of them. Right? And then we apply DIPCA. This time I used a high lag just for illustration purposes. I mean, you can use a high lag of thing to get more accurate estimates of this if you wish. And you do apply hypothesis testing, all the usual rigmarole, and you'll get the order correctly. You'll find the number of constraints correctly. From there, you can estimate the order, and the order turns out to be 2. Okay, and correctly, the hypothesis test actually correctly identifies the order to be 2, and also it gives you estimates of the sigma square, both the for the output and the input. Okay, and they turn out to be fairly close to the actual value. Again, we have done Monte Carlo simulations to show that you get unbiased estimates of the confidence interval. 95% confidence interval of the estimates contains the true value in both cases. And you can also here I've shown the 95% confidence interval for the individual coefficients. You can see that the first term is 0, essentially indicating that that is insignificant. And I'm sorry, the first term is insignificant, whereas the second two terms actually contain the true value. So they're all unbiased estimates that you get. Okay. And that is true of all those coefficients for yk minus 1 and yk minus 2. So these are all the standard application of DIPCA that we did. And once we have done this, we basically did two things. First is, it is very one of the tempting to use directly PCA to obtain the estimates, because PCA, despite the fact that you know it only as a compression tool, there are basically three interpretations of PCA you can give. One for dimensionality reduction, which is the usual thing that everybody uses. The second is for what we call model identification, the constraint model. So while compression deals with identifying the eigenvectors corresponding to the largest eigenvalues, it worries about that. It uses that to do compression. Model identification looks at the eigenvectors corresponding to the smallest eigenvalue. In fact, we have shown that all the small eigenvalues should be equal to each other. And we also identify the number of constraints or number of PCs to select or discard, as the case may be. Right? Those are the two interpretations we have seen. The third interpretation we have not dealt with is what we call filtering or estimation. So PCA itself can be used for denoising. Why? How come? Because there are constraints that relate the variable. Therefore, it is possible to obtain what we call filtered or estimates of the input and output from the data, which is better than what we have, by exploiting the redundancy or the equations that relate the input and output. So along with the model identification, you also get what we call estimates for each column. Okay, remember PCA deals with the matrix where each row is a sample and each column is a variable. It looks at them as distinct variables, and corresponding to each of these columns and each time instant or each sample, you get estimates. And these estimates are nothing but can be derived from the retained PCs, if you will. The first term of the SVD, U1, S1, V1 transpose, what you retain, that gives you the estimates. You can prove this. It is optimal in the least squares, total least square sense, which is nothing from a point of geometry. If you look at your total least squares regression, it's basically the foot of the perpendicular represents the estimate. We also saw that both the two variables are adjusted, and the adjusted values are nothing but the foot of the perpendicular that you draw from the data point to the line, regression line. It's the same thing here. You have a data space defined by the eigenvectors corresponding to largest eigenvalues. You project it, do a perpendicular orthogonal projection of the data, and the foot of the perpendicular represents what we call the estimates. And these estimates, if you try to use, you will get into a problem because we are using lag variables in the dynamic case. So if you look at, unfortunately, I don't have the thing and I can't write on the screen, but if you look at the first column, it contains yk minus 1, uk minus 1, and so on. And the second column also contains yk minus 1. Starts with yk minus 1, contains yk minus 2. So the variables yk minus 1 is repeated across columns. Yk minus 2 is also repeated across several columns. Typically, it will have eta times, it will repeat roughly. So all the variables repeat, and for each column, you get an estimate, and these estimates are not identical. PCA, unfortunately, doesn't realize that these variables are same. So it derives an independent estimate for each of these variables at each instant of time. So here I plotted the estimates derived from two such columns for, let's say, for one of the variables, output variables. This is the output variable estimates derived from two of the columns. Okay. And you can see that one of them is quite different from the other. So first of all, you get non-unique estimates if you try to just rely on the PCA estimates, which is very tempting. Okay, that's the first thing we try to look at, but that is not does not give you unique, and obviously because it's non-unique, it's also not optimal. So multiple estimates for the same variable at each time instant, they are non-optimal. Okay, so we basically don't want to use it. Whereas if you convert it to a EIV state space form, okay, or standard state space form as we saw, then we can apply the Kalman filter and get unique estimates, which are also optimal in the sense that Kalman filter actually thing. Either you can look at it as optimal maximum likelihood estimates or optimal a posteriori estimates and so on. Okay. So now here we have shown the estimates obtained for the output variable for this CISO system and compared it to also the true values that's used in the generation. And you see that fairly a good match that you get. And we also computed the residuals, and they have shown the plot in the bottom figure. So essentially the residuals are the innovations. If you will, I am only looking at the output residuals. We are not looking at input residuals. You can also get input residuals, but those are not very useful. At this point, we are not going to worry about it, because in the special case when D is 0 and when there's no correlation between the error variances in U and Y, you will show that the estimates for you is just exactly the measurements themselves. You can't filter them. You can't do much about the inputs. Okay, unless there is some additional information, and that information will come only from D if there's a direct feedback. If there's no direct feedback and there's no cross correlation, there's no way of improving the estimates, and therefore you will not get the filtered residuals for U will be 0 in that special case, and that's the case most often. Okay, so we are only worried about the output residuals, and we can use this. We can see that is 0 mean, which is what we expect roughly. I mean, this is eyeballing it, but the best thing is to actually compute the autocorrelation function of these residuals and see how they look. And here is the autocorrelation function for this particular model, identified model. And you can see the autocorrelation function lies between the limits that you actually expect for this particular thing. I mean, if it is a 0 mean white noise, that's what this is basically showing. Now, the thing is, in this particular case, we have got the order correctly. And therefore, the autocorrelation function also confirms that perhaps what you have estimated is correct, the model order and everything. Okay. Whereas let's see the case when the model order is not estimated correctly. So let's take another example. This is a 5th order system. And here what I've done is deliberately used a 4th order model. So when you apply DIPCA to it, actually it turns out that whatever lag you use, 15, 20, whatever you use, it correctly identifies the order as 5. Rarely it goes wrong. Unless you use a very large lag, we don't notice DIPCA itself failing. The hypothesis test usually picks out the order correctly, the number of constraints correctly, and hence the order correctly. But here, we're deliberately chosen a wrong order, applied DIPCA with this order given, and estimated the coefficients, and then computed the Kalman filter residuals for this model, converted to the state space form, and then applied it. And here you can see the autocorrelation function flagging that something is wrong with the model. You can see that the ACF values at lag 3 and lag 6 and so on are actually going out of bounds. In fact, several of them have gone out of bounds, indicating that perhaps the model order is incorrect, right? So in this particular case, you have a secondary, if you will, you can do a residual analysis to catch this problem. In case DIPCA makes a mistake, usually the mistake is just by, instead of order 5, it might actually come up with an order 4, in which case you actually can use the ACF to catch it and probably increase it and redo the thing and verify whether the ACF is correct. Okay, so this is a secondary, as a backup, you can look at the ACF. Obviously, if you overestimate the model order, if you instead of 5, you make it 6, the ACF will not flag it. Typically, underfitting or underfitting model, process will actually give rise to this kind of patterns, but overfitting, if you use a higher order model, like instead of 5, you use 6 or 7, the ACF may not flag. Okay, so typically underfitting at least can be caught. And the way we do the DIPCA is start with a very first order model guess. We start with the high value of D and gradually reduce it. So in our process, typically underfitting might occur, but overfitting rarely occurs. Or as I said, most of the time the order is correctly identified, but even in case it misses, the way we have constructed the thing, only underfitting will occur most thing. If at all it makes an error. And in that case, the ACF will flag it and we can correct it. So we have a good, what we call checkpoints to actually figure out whether the model order is estimated correctly. So I'll just kind of close out that what we have done is order estimation performed in DIPCA using a sequential approach starting from a low order system guess. For large lag, it may underestimate the order, premature termination of the sequential hypothesis test. But in that case, that we can use the residual computation from EIVKF for validating the system order. We are only looking at the output residuals, as I said, or the innovations, standard innovations of the Kalman filter, and using the ACF in order to trap it. And if that is underestimated, if you feel that the ACF is indicating that, then you go back and increase it and re-estimate and double check. Okay, so that's one iteration you can do if you wish. And that's exactly what this is useful for. Although we have used the residuals only for validation, in general, once you have obtained the model, these residuals are also useful for fault diagnosis and things like that. You can actually use it for identifying, let's say, biased measurements using fault diagnosis tools. So not only that you can actually do this for model validation. It has much more wider applicability. And more importantly, because DIPCA also estimates error variances, you can apply all of this. If the error variances were not available, you can't do the same thing. You know, you have to, you can't, apply a Kalman filter or get any of these. So that's also an important piece of information that's coming from DIPCA, which can be utilized for, let's say, other applications like diagnosis or even what I call control and so on, right? So that's, I'll close with this. I mean, if there are any questions, I'll take them. Slightly exceeded the time now. Any questions on this? So typically in classical identification, they use residual analysis in a very similar way. They look for two things: autocorrelation of the outputs and also of the residuals, as well as the cross correlation between output and input. We have not used the cross correlation because I think we still have to check what kind of property it should have in the EAV case. So that's one thing that we need to counter check before it can be used. Okay, so we are left it at this point. We are using only the ACF thing to figure out whether the system order may be estimated incorrectly by DIPCA and catch it specifically underfitting. Anything you want to add, Arun?
No, just a small correction. It is actually cross correlation between residuals and inputs.
Yeah, residuals and inputs. Yeah.
Yeah, not between outputs and inputs.
Yeah. But we have to check first the residuals and inputs are not correlated in the EAV case. We have to ensure that.
Yeah. So the typical what do you say, the sequence of tests that we conduct in classical identification is first to check for cross correlation between the residuals and the inputs, and then we look at autocorrelation of the residuals, because we want to make sure that the deterministic model has been estimated accurately first, and then the autocorrelation of the residuals is to verify if the stochastic part has been modeled correctly. So here we are not per se using the residuals for checking the goodness or performing the goodness test for deterministic part. We are only believing, because we have already fixed our mind on the fact that the errors are right. We believe that if we make a mistake in the deterministic part, that will reflect the residuals. But in a strict sense, yes, we should first look at the cross correlation between residuals and inputs, but we'll have to evolve a mechanism or criterion, because what we will have in EIV cases, error prone inputs. So what is it that we should expect in terms of cross correlation between residuals and measured inputs is something that we'll have to work out. In general, anyway, DIPCA will make sure, I think in DIPCA, if you do things properly, more or less, you are guaranteed correct model order estimation.
So can I take it that there are no further questions?
Yeah, I do not see any questions in the chat window, or I do not see any raised hands.
Yeah, looks like there are no questions.
Okay, then I think we'll meet again in the evening too.
Yeah, at 5 o'clock.
Yeah,
right. Yeah. So before that, the upcoming event is our final plenary talk at 2 o'clock.
Okay.
So I hope I'll see you there.
Sure.
Okay.
All right. Bye bye.
Thank you.
Thank you.
Thank you, everyone.
Take care.